everyone. So today we are going to talk about the Cayley Hamilton theorem. So the theorem states that every square matrix satisfies its own characteristic polynomial equation. Now basically we have to first understand what is the characteristic polynomial. So the characteristic polynomial is associated with the determinant of the matrix and the eigenvalues. So we write determinant of the matrix like this, and we represent eigenvalues with this particular symbol, which is called lambda, as you already know. So how do we write this statement in symbolic language? For this, first you have to construct the characteristic polynomial. So the characteristic polynomial is the determinant, which is written like this: a minus lambda I, where a is the given matrix, lambda are the eigenvalues, and I is the identity matrix or unit matrix. So what is the meaning of this statement that the matrix satisfies its own characteristic polynomial equation? It means that the value of this particular determinant is equal to 0. So if we have the value for A, that means we are given a matrix A and we construct this equation and then the subsequent determinant, right? If we substitute the value of A in place of lambda, we are going to find that it reduces to 0. Let us do this by means of an example. So let's say that we are given a matrix A equals to 1, 2, 3, 4. Okay, now what we are going to do, we are going to construct this particular characteristic polynomial. So we will write this as a minus lambda I is equal to 1, 2, 3, 4 minus lambda times 1, 0, 0, 1. So this is the identity matrix which has the same order as the matrix for which we are going to prove this Cayley Hamilton's theorem. Okay, so now we are going to write this as C1 minus lambda. So already we have seen the matrix addition and subtraction, so you can go to that video and check it. So 1 minus lambda. Now 3 minus lambda times 0, that is 3. Then 2 minus lambda times 0, that is 2. Then 4 minus lambda times 1, that is 4 minus lambda. So this is our matrix A minus lambda I. Now I want to find out the determinantal value of this matrix, which is our characteristic polynomial. So we need to expand this. So to expand this, you can use the traditional method, that is multiply these two terms and minus the product of these two terms, right? Evaluation of a 2 cross 2 determinant. Or you can also use the shortcut technique for expansion of a determinant. So we have 2 cross 2 determinant. So the first term in the polynomial is going to be lambda square minus trace of the matrix. So trace of the matrix is basically the sum of the diagonal elements, the leading diagonal elements, which is 1 plus 4, that is 5, minus 5 lambda, plus the determinantal value of this matrix, which is, if you expand it, 4 minus 3, that is 4 minus 3 times 2, sorry, that is 4 minus 6, which will be minus 2. So in short, our characteristic polynomial is going to be lambda square minus 5 lambda minus 2. Now what we are going to do, since we want to prove the Cayley-Hamilton's theorem, in place of lambda we are going to substitute this particular matrix which is A, right? So I am going to write this as A square minus 5A minus 2. Now I just can't subtract 2 from matrix value. So I have to write this as 2 times I, which is the identity matrix. Okay. So now what I'm going to do, I'm going to substitute the values of A square, 5A, and then after that 2 times I, and then we'll see what the resultant will be. So here A square, so A into A, so we are going to do matrix multiplication. You are advised to do this multiplication on your own. 7, 10, 15, 22. Now minus 5 times A, so you are going to multiply all these values with 5. So you're going to have 5, 10, 15 and 20. So now we are going to write this as 5, 10, 15 and 20. So A square minus 5A minus 2 times I. So this is I is the identity matrix 1, 0. Over here we can see 1, 0, 0, 1. So I'll write this as 2, okay, 0, 0, 2. And now once again we are going to do matrix addition and subtraction. So 7 minus 5 is 2, minus 2 is 0. Now 10 minus 10 minus 0, again 0. Now 15 minus 15, okay, minus 0, that is again 0. Now over here we are seeing 22 minus 20, that is 2, and 2 minus 2 again 0. So in short we are getting a 0 matrix. Therefore what we have done, we have proved the Cayley Hamilton's theorem. So therefore A square minus 5A minus 2I equal to 0. In other words, the determinant which we were evaluating, which determinant, A minus lambda I, okay, that is equal to 0. Determinant of A minus lambda I is equal to 0, and hence we have the Cayley Hamilton theorem has been satisfied. So what is the statement of the Cayley Hamilton's theorem? Once again we'll just look at it. Every square matrix satisfies its own characteristic polynomial equation, which means that we have to prove that modulus of A minus lambda I is equal to 0. So we just saw an example where we have proved the Cayley Hamilton's theorem, right? So hope you have understood. Thank you for watching.